Thanks, David.
Thank you. Thanks everyone for being here. I'll talk about reflection principles in first order set theory with Ward elements. I guess I'll focus on reflection in ZFC with Ward elements because most of the things about reflection without choice are still unknown. But I'll talk a little bit about them at the end. Let's see. All right, so so Ward elements are things without members and they're not sets. Set theoretic universe with Ward elements look something like this. So at the very bottom you have a class of Ward elements, might be a proper class, might be a set. Then you can generate sets of Ward elements and sets of Ward elements, etc. So this universe can be seen as a universe that includes absolutely everything, right? Which might interest some philosophers. And so here we have sets whose transitive closure doesn't have any Ward elements in it. Those are sets are called which are called pure sets, and so this is the universe V, and this is where
Yao Bokai, your slides is just in the first page. We didn't see this.
So can you see the? Is it moving right now?
No.
Oh, then maybe I'll stop sharing and I'll share it again. Okay. Oops. Can you see my slides right now?
Yes.
Is it moving?
Oh, yeah. It's moving. Yeah.
Okay, cool. So yeah, so this universe U, which I was talking about, it includes sets and non-pure sets, also Ward elements. So here is the universe of all pure sets called V, but I'll call the whole universe U. So the Ward elements become redundant when set theory is treated as a foundation. So that's why most of the time set theories don't talk about Ward elements at all. But it's still interesting to ask, well, how different is U from V, and what are the axioms for U? So these are the questions I am interested in. So let's recall the Levi-Montague reflection theorem in ZF. So it basically says that for every formula, you can find an arbitrary large V beta such that phi is absolute between V beta and V. Well, we can ask, well, will this reflection phenomenon also appear in U, the set theoretic universe, which includes everything? Well, let's first fix a theory for U, right? I'll call this theory ZFCU with replacement. So this language L, A epsilon will be the language that extends language of set theory with a unary predicate A for Ward element, double struct A. We say X is a set just in case it's not Ward element. And so and we need to modify some of the axioms of the FC for them to make sense, right? For example, extensionality in this context, we say any two sets with the same members are identical, and we don't want any Ward elements to be in the power set of X. So we do some adjustments. Then ZFU with replacement is this theory. And ZFCU with replacement will be ZFU with replacement plus AC. So key thing here, so REP here indicates replacement, and basically it indicates that we're using replacement instead of the collection principle, which will be important later on. And it's not assumed in either of these theories the Ward elements form a set. So A here could be a proper class always. Well, the FCU or with replacement seems to be a very natural set theory with word elements, because we just have these axioms of the FC and we make some straightforward modifications. Well, or is it? Let's find out. So in the context, let's think about reflection in U. So reflection with word elements in general. So in the context of word element set theory, we can't expect V alpha or V of A, which is the hierarchy built from a set of word elements A, to reflect, because in the universe there might be a proper class of word elements, but in sets like these, they all think there is a set of word elements. But we can still hope reflection happens for transitive sets. So I'll call this principle CRP. It says that for every, well, basically the Levi Montague reflection would be a special case of this, right? It says that for every formula phi, you can find an arbitrarily large transitive set such that phi is absolute between this transitive set and the universe. So C here is for complete, because we have, because here we have this biconditional here. And we can also have this kind of partial reflection principle, which says that whatever is true, basically, is true at some transitive set. Okay, so whatever is true is already true in a transitive set. So we can ask the following questions, or, well, are they provable when there are word elements, or are these two forms of reflection equivalent? Another two commonly seen principles, collection principle. It says that if every x bar, x in x bar has this y, some y such that x and y have this phi relation, then you can collect them. So there will be a y bar such that for every x in x bar, there's y bar such that x and y have this relation phi. And DCS is the dependent choice scheme. It says that if you have this phi relation, which defines which doesn't have a terminal node, right, which is total, then you can have this infinite ascending chain. Collection is provable in ZF, and DCS is proved. So DCS generalizes the idea behind dependent choice, and it's provable in ZFC. So we can ask, are they also provable in ZFCU with replacement? So it turns out that in ZFCU with replacement, these questions can be answered by looking at some principles concerning word elements. So let me introduce my notation here, which shouldn't be confusing, I think. So uppercase ABC should always stand for sets of word elements. This double struct A should always stand for the class of all word elements. So it could be a set, it could be a proper class. And U here will stand for the class of everything. We say a cardinal kappa is realized by A, just in case A is eponymous with kappa, and we say kappa is realized if A is realized by some set of word elements A. For every word element, set of word elements A, the tail cardinal of A is if it exists, is the greatest cardinal kappa realized by some B, which is this one. Right? So the idea is that, sorry. Idea is that, I won't draw a picture, but anyways. Okay. So the idea is that if you have a set of word elements, there might be different sets of word elements that are disjoint from A. But in some cases, there will be a largest one in terms of its cardinality, right? And we call, if that's the case, we call the cardinality of that set the tail cardinal of A. Okay. Is everything all right? Is it moving? Okay, cool. So with these definitions, we can introduce some principles. So plenitude just says that every cardinal is realized. So there are unboundedly many sets of word elements. scatter, it says for every A and a realized cap, there's a B of such cap that's disjoint from A. Closure, it says that X is a set of realized cardinals and the supremum of X is also realized. Tail says that either plenitude holds or every set A has set of warrants A has a tail cardinal. So the main result here is that we can prove this implication diagram in ZFCU with replacement. And this diagram is complete, meaning if diagram doesn't show that phi implies psi, then we can find a conflict model. So, well, some of the directions are not really hard, but I want to talk about this relation between collection and CRP complete reflection. So let me review some basic definition of facts. So for any set of elements A, we can build this hierarchy as Euro. And for every set X, so the hierarchy will be of A. For every set X, the kernel of X will be the set of elements in the transitive closure of X. Basically, you can think of kernel of X as the set of elements that we need to use to build X. And X is in V of A, just in case its kernel is included. And the models of ZFCU are not rigid. There can be many non-trivial automorphisms if there are like one-on-one elements. So for every definable permutation, in particular pi of A, it can be extended to the universe U by this epsilon induction, and this will be an automorphism. And if pi pointwise fix the kernel of X, it will fix X. All right, so let's think of this question: when will collection hold in U? So collection does not necessarily hold in U if our background theory is the FCU with replacement. But we can observe that if A is a set, the class of overelements is a set, then everything, then this hierarchy makes sense. Then everything is in this hierarchy, so collection will hold by the textbook argument. And in general, we can also show that if closure and scatter hold, then collection will hold. I'll go through this argument really quick. So let's suppose closure and scatter hold, and for every X in X bar, there's Y 5 X bar. And we want to find the Y bar that collects. Well, for every X in X bar, that state X be the least cardinal, which is realized by the kernel of some Y, such as 5x1. Okay. And let theta be the supremum of the set of these cardinals. And we may assume omega is realized because we may assume the word elements do not form a set, otherwise collection will hold by this operation. So A will, double struct A will be a proper class. In that case, for every n, finite number n will be realized. So by closure, omega will be realized. So every cardinal in this set will be realized. So by closure, again, the supremum of the set is realized. And by scatter, this kernel will be realized by some B, which is destroyed from the kernel of X bar. So we'll let A be the union of this set B and kernel of X bar. So we're gonna collect things in B of A. Now let's consider any X in X bar, right? There are some Y such as phi of XY. Well, among those Y's, there will be some Y star whose kernel is the least possible. Okay. And by the definition of B, we know that we can move union of kernel Y star and B bijectively into B because B is big enough. So we can do this. And we can also extend this bijection into automorphism. without moving anything in X bar. I will not go through the details, but we can do that by scatter. So the resulting automorphism will move at Y star into V of A and doesn't move anything in X bar. So in particular, it doesn't move X. So that means for every X, we can find a Y in V of A such that 5x1. But X bar is set, so we can go high enough in V of A, find an ordinal such that V alpha of A will be the collection set. So this shows that if closure and scatter hold, collection will hold. All right, so by pushing this kind of argument a bit harder, we can show that tail, which says that either plenitude holds or every set of Word elements has a tail cardinal, also implies collection. Well, we should need to show two things, right? First, if plenitude holds, then collection holds. But if plenitude holds, then closure and scatter will hold. So by the argument before, we will know that collection holds. So, and by pushing the argument harder, we can show the other case also implies, the other situation also implies collection. So we can also show that if tail holds, then the dependent choice scheme will hold. So we have this diagram here. Now we want to show that collection implies CRP, the complete reflection principle, so we can finish the circle, the circle. So in this paper by Dickman, Hampkins, Johnstone, they show that over CFC without power set, collection dependent choice will give you the complete reflection. I will just go through this argument really quick to show that it also works in CFCU, its replacement. So so consider formula phi, and we list all its subformulas, and we see Z is a phi cover of X, just in case it's a transitive set extending, sorry, typo here. Z is a transitive set extending X, and the following holds for every I. Namely, if you have if there is an witness for phi I, then you can find that witness in set Z. By collection, we can show that every X has a phi cover, because you can just consider the set of all finite sequences of X. Then by collection, doing collection for K times or K plus 1 times, then you can collect all the witnesses. Then you take the union of that collection set with X, and you take the transitive closure of that union. That would be a phi cover of X. So by dependent choice scheme, that there will be an infinite ascending chain such that Tn plus 1 is always a phi cover of Tn. Then we can take the union of all these Tn's. That would be a transitive set such that phi is absolute between T and U by the Tarski-Walk test, basically. Okay, so collection implies tail implies DCS, but the collection and DCS together implies CRP. So collection gives you CRP, so everything works. Now we want to show the diagram is also best possible. So we always from now we always assume a double struct A is not a final set. So let I be a definable class of subsets of A. We say I is normal ideal, just in case it's an ideal, and it contains all the singletons. But in most of the cases, we're interested in a double struct A will be an infinite set. So this is definition of normal ideal. Basically, it picks out a bunch of small sets of it. small subsets of A. Then given normal ideal I on A, we can define this inner universe UI, which consists of all the sets whose transitive closure is small in the sense of I. And the class of elements in UI will always be a proper class. The theorem here is that if we assume that U is replacement and let I be a normal ideal on A, then ZFU with replacement will always hold in UI. And if AC holds in the background universe, AC will always hold, will also hold in UI. Most of axioms are not hard to verify because I is ideal. We use normativity here to show that replacement holds in UI. Okay, then we can build models to show diagram is best possible. So I'll just talk about first three of them. So first one, start with a model of ZFCU with replacement with only comfortably many elements, and let I0 be the finite ideal. Then UI0 will be a model of ZFCU with replacement by the theorem. Then the closure, you can see that. Then closure will fail because every n finite number n is realized, but omega is not. DCS also fails because for every x there's y with a bigger kernel, but you cannot have an infinite descending chain. Otherwise, the chain itself will have an infinite kernel. But everything has a finite kernel in this model. So also in this model, collection fails. Okay, second one, let's start with omega 1 many elements and take the countable subset, idea of all countable subsets of A. Then in the model UI1, every set of elements is countable. So omega 1 is the greatest realized cardinal. So that means closure must hold, but the plenitude fails. Scatter of course holds because if you have a countable subset, it will be another one that's destroying the way. So this shows that closure and scatter doesn't prove plenitude. So let's show that tail does not imply scatter. Against start with omega 1 many elements. Fix another set of elements of size omega 1 whose complement is also omega 1. And let I2 be this ideal. It consists of all the subsets of A who such that B minus A is almost is at most countable. And for every B in this model UI2, this cardinal here will be the tail cardinal B. But scatter fails because, well, A is in this model. This single stroke A is in this model as a set. And omega 1 is realized because A has size omega 1. But there's no set of elements of no uncountable set of elements that's destroyed. Okay, so the immediate corollary is that nothing on this diagram is provable in the FCU or replacement. Well, we may conclude that the FCU with replacement is too weak for a set theory elements because obviously, especially if we have axiom choice here, we would want most of things on this diagram to reach. So I want to mention this similarity between ZFCU replacement and ZFC minus ZFC without power set. In their paper, Gateman, Hampkins, and Johnstone, they showed that if you axiomize ZFC without power set, only with replacement, but without collection. There are lots of disastrous situations. For example, omega-1 could be singular, and so on. So they conclude that that theory is just the wrong theory, and instead, by ZFC power set, we should just mean ZFC without power set, but with collection. So here we might say the same thing to set the ZFCU, right? Because with given that diagram, we know that with collection, ZFCU with replacement can recover many desired theorems, such as the complete reflection principle and the omega dependent choice scheme. So I would like ZFU denote this weak theory with collection, and ZFCU would be ZFU with AC. This is the theory we'll be using later. Okay, but here's a note. There is also a decent analogy between ZFC minus and ZFCU. So, for example, ZFCU doesn't prove the omega-1 DC scheme, which is a generalization of omega DC scheme. But this scheme is provable in ZFC. So just consider a model where every set of Ward elements is countable, but there's a proper class of Ward elements. For every set X, there is Y with a bigger kernel, but it cannot be an omega-1 descending chain. Otherwise, the chain will have an uncountable kernel. So this shows that DCS with omega-1 fails in that model. Also, this so-called injection principle, which says that if you give me a class, if you give me a set and give me another proper class, there will be an injection from that set to that class. That principle also fails here. So it's also not a theorem of the FCU, even we have collection already. All right, I'll talk a little bit about reflection without choice. So maybe I should note that ZFU is a more interesting set theory with Ward elements, because if you have ZFCU, or if you have choice here in U, then every set of Ward elements can be well ordered, then it's equinumerous with a pure set. Then why don't we have these sets of Ward elements at all, right? We can just talk about their isomorphic copies in B. So maybe set theory with Ward elements is only interesting when there are sets of Ward elements that cannot be well ordered. And we can also insist AC in B, right? You can have a non-well ordered a set of Ward elements that are not well ordered, but you can insist that every pure set can be well. Okay, so maybe ZFU or ZFU with AC for B is a better theory. So let's think about reflection in this context. Well, in pure set theory, reflection is provable without choice. It has nothing to do with choice. But our earlier proof of CRP from ZFCU makes use of choice, right? Because we have to use this DC dependent choice scheme to prove reflection. But to have dependent choice scheme, at least you need dependent choice. And I believe you need more in this case. But this argument can be improved. So let me make two more definitions. So we see a set of Ward elements A has the duplication property. If every B that's destroyed from A, there is a typo here. There is another C that's equinumerous with B and destroyed from the union of A. And A is, for the lack of a better word, universal if every set of Ward elements B is equinumerous with some set in the other. And in this recent joint work with Joe Hampkins, we show that if we assume ZFU without choice, we can and with with a set of elements A that is universal and has a duplication property, then the complete reflection principle will hold. The assumption of the theorem is a consequence of AC, but it's even weaker than the complex. So that's an improvement. But in general, lots of things are still unknown. So these questions are all open. For example, does AFU prove CRP? We don't know the answer. And does AFU prove the partial reflection principle? We don't know. Are these two reflection principles equivalent over ZFU? We don't know. And we can even strengthen ZFU a little bit by adding dependent choice. But we don't know if this theory proves CRP or RP, or even dependent choice scheme. So yeah, there are lots of things to explore in this area. I hope this might interest some of you. That's it. Thank you.
Okay, thanks. Thanks for the talk. So any questions?
Or maybe
There's no questions. So okay, then we will start the next talk about 25 minutes later. Okay, thanks for